Hi, everyone. Thanks for joining today's webinar on the numbers behind the measurement. I'm Robert Grotans, the Global Technical Marketing Manager at X-Rite, and I will be moderating today's webinar. Presenting today is Tim Mao, our Applications Engineer and Technical Support Manager. A few things to go over before we get started. Due to the number of people that are attending today's webinar, we will keep everyone muted. During the webinar, if you have questions, please use the questions function on the GoToWebinar panel. I'll be monitoring the questions, and at the end of the webinar, we will have time for a short Q&A session. Finally, this webinar will be recorded, and you'll receive a link so that you can review the webinar at your convenience. I'll turn it over to Tim Mao to start things off.
Thank you, Robert, and good morning, good afternoon, good evening, depending on where you are. Welcome to this webinar as we talk about the numbers behind the measurement. In other words, where do those numbers come from and what exactly do they mean? So we've got lots of good material to cover today, so let's dive right in. Our agenda today is basically three topics. First of all, we're going to talk about why we use numbers. Then we will talk about the source of those numbers and where they specifically come from, pardon me. And then lastly, relating those numbers to what we see. We've all been looking at color our whole lives. If we can't correlate the numbers to what we see, then the numbers aren't terribly useful. So let's get started. So why we use numbers? There are a number of reasons, but I'm highlighting three here today. One is that color is a psychophysical human response. We as humans have been looking at color our whole lives. We react to it in different ways based on our experiences, our life experiences, and so forth. And they cause us to see color in different ways. And so we're going to start out with a little test here. We're going to see pop a poll up here. We're actually looking at something with two squares, an A and a B. Some of you may have seen this before and know the answer, but we'd like you to answer in the poll whether or not you think A and B squares are the same color. So I'll give you 10 seconds to answer that. All right. So, as you may have suspected, even though you might not have believed it, they are indeed the same color, and there you see it. A and B really are the same color. That's really hard for us to process as humans because of our experience. We know squares aren't the same color, dark squares aren't the same color as light squares. That's just the way things are, but it appears that they're very different even though they're the same. Let's move on. Color is also both an art and a science. It's a unique blend of those things. And the artistic part of color, we can use as an example this painting, which has colors in it to try and elicit emotion from us. Maybe it causes us to have memories about things. It's impacting us, and the color impacts us. Colors can cause us to remember things, can cause us to have mood changes and those kinds of things. And so it can be difficult for us to see color the same in every situation. But it's also a science. We all know, probably did this experiment when you were in school, putting a light through a prism and you see all the colors come out. A rainbow acts as a prism and does the same thing. But the colors that come out are essentially contained in the light. Light really is color. And so if we know that and we can measure the various wavelengths of color, you see those displayed from 400 to 700 nanometers, from violet to red, we can then potentially measure that and put some science to the color. Doesn't negate the art and the emotional side of it or the human side of it, but it does allow us to measure it. And of course, do it without the influence of our mind, state of mind, or our mood. And the last reason we use numbers is because words aren't an accurate means to describe color or color difference. In fact, words aren't an accurate thing to describe lots of things like temperature. There's two words up there, hot and cold. And depending upon where you live, what you think is hot or what you think is cold might be very different. For example, if we go to someone in Anchorage, Alaska, and ask them what temperature is hot, or cold, honestly, it's going to be a very different answer than if we go to someone in Atlanta, Georgia, or if we go to someone who's in the Sahara Desert, their answers will be even probably greater difference, right? So we can argue about what's hot and what's cold. If you're like me, you sometimes have that argument with your wife. It's too hot in here, or it's not hot, or it's too cold in here. When we talk about color, sometimes we use words like dirty and clean to describe things, or we could be describing the cleanliness state of the table, right? Is it clean or is it dirty? Our perception about those things can be very different from one person to the next. What we don't argue about is what that means. 7.5. There's no disagreement about what that number represents. Everyone understands it. In fact, the beauty of numbers is we don't even really have to translate them from one language to the next in order to communicate what that means. So there's good reasons for us to use numbers. We lose something when we do that, for sure. We lose the art and the psychophysical piece of it a bit, but numbers are a concrete way for us to describe things. So let's talk about the source of the numbers. So there's really 3 steps involved here. And the first step is using a spectrophotometer to measure the object, and we're going to obtain spectral data, also known as reflectance or transmittance percentage. So a spectrophotometer, a simple view of one, there's lots of different ways they can be configured from how the light is presented, but basically, spectrophotometer shines a light on an object. As we know with the prism experiment, the light contains all the colors. So then what we're measuring through a series of filters or various mechanisms of filtering light, each of the individual wavelengths, and the result is we get this reflectance curve. And that curve, that red line representing this pinkish color that we measured, is actually a graph plotting, in this case, 31 measured points. So we've measured every 10 nanometers from 400 to 700 nanometers, and we can plot a reflectance curve. So now I've got some numbers that represent that color, but there's 31 numbers that are percent reflectance that really don't relate a whole lot to what I see. So I've got to do something more with those numbers. But these are the foundational numbers of this color. The measurement of that data, if I get 2 reflectance curves that match, then those 2 colors will match under every condition I can put them in, because essentially a reflectance curve, that reflectance data is the fingerprint of that color. Step 2, now we're going to convert the spectral data to tristimulus data, which is a fancy way of saying 3-dimensional color space. Commonly, people are using LAB or LCH as a color space, a 3-dimensional color space. So let's talk about that for a second. How do we get there? Well, it starts with a light source, right? So we have to account for the light. Why do we have to account for the light? Because different light sources cause color to appear differently to us. As an example, here's a picture of a light booth. It's got what's called a color checker in it, that thing with all the little colored squares in it, and you can see the grayness of the back panel of that light booth. That's what it looks like with simulated daylight turned on. Now the next 2 photos I'm going to show you are the exact same light booth, everything the same in it, except we changed which light was turned on. So that's what the colors look like if we use fluorescent light. And lastly, that's what the colors look like if we use incandescent light. And you can see there's a vast difference in the color of the background of the booth, the color of those color swatches. If you look at the grays across the bottom on the far left, and then look at the grays on the far right, and they aren't even grays anymore. They look like browns or that kind of color. So a light booth is very important. So we're going to pop up another poll question to ask you, are you, when you do visual assessment, using a light booth or some kind of means of controlling the light? So we'll give you a couple seconds to go ahead and answer that. All right. So it's obvious by looking at this picture that we have to account for the light. So we account for the light source in the calculations we're doing. We account for the object. Obviously, we've taken a measurement of it, like we just talked in step one. We've got the spectral data, and we've got data to represent the observer. Now, we're not going to go into the whole tests and everything that were done to identify the human part of color, but suffice it to say, we have data that represents how the human eye reacts to each of the various wavelengths of color, so that we can incorporate the human part into these calculations. And then ultimately, if I'm measuring that yellow school bus, I'm going to get some what are called XYZ values that will indeed define it as yellow. XYZ is not terribly relatable to the eye, so we've got one more step of calculations we do with XYZ that converts it to either LAB, which you may be using, or LCH. And now we have this three-dimensional color that we can, three-dimensional system that we can use to describe the color of that bus. But we're not done, because of course, measuring something to identify what color it is isn't terribly useful, because we can look at the bus and see that it's yellow. But if I have two buses or two parts of that bus that need to be the same color, I need to now be able to do step three, which is calculate the difference between your standard or your target and your sample or your trial that you're working with. I need to be able to calculate that difference to be able to determine if the difference between them is enough to be acceptable or unacceptable. And the way that happens is actually fairly simple. You plot the location of the standard. Here I'm using LAB color space, and you plot the location of the sample, and then it's a simple means of subtraction to calculate how far away are they from each other. Is the sample redder or greener or bluer or yellower than the standard? Is it lighter or darker? And we can determine that by looking at the values that we get when we do those calculations. So, if my delta L, that's what the lowercase d with the L next to it, right, indicates. I can now calculate, if the delta L number is a negative number, that means my sample is darker. If it's positive, it's lighter. The A, if it's negative, it's greener, and positive is redder, and so on through this list. And you'll notice when we get down to delta H, it doesn't tell me whether the thing is red or blue or yellow or greener. It just tells us clockwise or counterclockwise. The reason for that, you'll notice with the asterisk and the note above, the descriptors for delta H depend on the location of the standard in color space. So if I'm looking at a red, which is potentially 0 degrees, and I'm describing a red's delta H, the descriptors might be yellower or bluer, right? If the hue angle is greater, it would be, or is clockwise, I should say, it would be bluer, and if it's counterclockwise, it would be yellower. But if I'm talking about a green, green can also be yellower or bluer, but now clockwise is yellower and counterclockwise is bluer. So it just depends on where that color falls in color space. So now I've got numbers to describe my color and also describe my color difference. And we're doing this with 3 numbers at this point. We will talk about where we get to with going to ultimately to a single number. We'll get there. So now let's relate those numbers to what we're seeing. So to start with, a question for you. Do we see color difference the same for all colors? In other words, if the measured difference is 1.5 units lighter, if I'm looking at a black, does 1.5 units lighter look the same as if I'm looking at a bright red or a purple or a light yellow, right? Is my sensitivity to the numbers the same for all colors in all places? Or am I more sensitive to some colors than others? So we do know the answers to this, but we're going to start by looking at a couple of photos. So they're not the greatest photos in the world, but they serve our purpose. So on this screen, on this page that we see with these green squares, the green square in the center is my standard. And the one above it is some degree lighter, below it is darker. To the right, we have redder, greener, yellow, or bluer. So those other 6 squares around the center one are off in one direction or another. Here we have a similar set, different color. The gray in the center is still my standard, if you will. The one above it is lighter, the one below it is darker, and you can see which ones are red or green or yellow or bluer. So we've got a poll question for you here. If you were producing those 2 colors, those were your 2 color standards, and those other squares represented samples or batches that you produced, would they be acceptable to you? So go ahead, take a minute and think about that. Give us your answer. All right. Just for your information, the delta values between the center square and any one of those other squares is 1.0 units. And so most people will look at that and say the greens all look pretty good. Granted, we're looking at a picture, but I can tell you from experience and having shown these pages of color to literally thousands of people, most people think the greens look pretty good. The grays look not quite as good. Maybe 1 or 2 of the grays is okay. It all depends. But to maybe accentuate that even further, this is the same thing, only now the difference is larger. And so you look at the greens, from my perspective, looking at that right now, I'd look at the darker one and say, there's no way I'm going to pass that. But there's one, or maybe the lighter one even actually looks okay to me, right? And you may have a similar experience. It's quite different when I look at a gray with that same color difference. And when I show people this, they're always like, well, those aren't like matches to the center one. That's like the beginning of a gamut of colors that's fairly large. All of those squares in the second group of 2 pictures have a delta value of 5. So it pretty easily demonstrates to us, am I more sensitive to some colors? Yes, I'm obviously, our eyes are all very sensitive to a neutral color like that gray. If a difference of 5 units produces not a bunch of grays, but a pink and a blue and a green and so forth, it's very different than what we would detect with a green. So how do we deal with that? Because we don't want to have a different tolerance for every single color we produce. Well, fortunately, there was some work done in the past to help us with that. A man named McAdams did some work where he had people actually take individual colors, and he gave them a stack of colors that were all relatively the same. And then he asked them to basically look at the color standard that he gave them and compare each sample to it. And if it looked the same, put it in one pile, and if it looked different, put it in another pile. This plot you see, which used an old color space that was being YXY color space back then, the dots inside each of those ellipses is where the color standard fell. And the ellipse is showing us everything that looked good to the eye was inside that ellipse, and everything that looked bad to the eye was outside. So first thing we notice is that they're not circles, right? So we don't see color in all, even with one color. If we talk about the green, the one that's got the little finger by it, pointing at it, our eyes are much more forgiving in one direction than another, right? The narrow direction going from left to right, if you will, would be the hue difference. So that green being yellower or bluer. Our eye is very sensitive to that. The longer dimension, going essentially up and down on that ellipse, would be chroma or saturation, right? More or less chromatic. And so our eye is more forgiving on that. Now, these are actually 3-dimensional. Lightness would be coming out of the screen toward us. And we found the tests found that the human eye is even more forgiving of a lightness difference. So what he proved is that for a single color, we don't detect difference in each direction the same, but he also proved that it's different for every color, as is very obvious by the size of the ellipse of a green to a blue to a red to a yellow to a gray. All those ellipses would be of different size. So that work was done back in the 1940s, but we actually moved on, to get my focus back here, to current means of calculating color differences using something called delta E, which, well, again, we'll dive into just in the next slide, to allow us to plot and calculate these ellipses, or ellipsoids, I should say, three-dimensional objects, to calculate what's acceptable and not acceptable in color. So a way to look at that, and this is coming from a piece of our QC software, we've got a rotated three-dimensional view. Really quick, the red dots are trials that, or samples that failed. That little blue dot is one that passed. You can see the green, yellow, blue, red, green, yellow, blue, I should say, sections of the LAB color space. You can see the white plane that's showing lightness. Then there's a green rectangle in there. That would be if we had plotted an LAB tolerance around my standard. And then you can see kind of a purplish colored ellipsoid. That's a delta, that happens to be delta E 2000 tolerance plotted around that sample. And if we had this as an interactive thing, we could actually rotate and look at where the samples lie relative to the color of the standard. So to make it a little more digestible, let's look at this. We measured a bright red color, okay? And we got LAB values, right? So our bright red color was measured. We got the reflectance data, step one. Step two, we did the calculations to convert it to tri-stimulus. We chose to do it in LAB, and we talked about needing to know what light it's in. Well, that's what that same exact color looks like under three different light sources. So under daylight, look at the difference in the L value under daylight to the difference under A10. A is for incandescent. F2 is cool white fluorescent. D65 daylight. So you can see the shift in the L value. In fact, in all of them, the A value, the B value, those values are very different from one light source to the next. Pointing out again, it's really important that we're consistent about the light source we use to calculate these numbers. And in fact, at the bottom here, just showing you two D65 comparisons. There were two tests done. We talked about the observer part. There's a 10-degree observer and a 2-degree observer. And again, you can see there's a difference there, significant difference between those two calculations. So all of these numbers came from a single measurement. We didn't remeasure anything. It's one set of reflectance data, but it's influencing our calculation in step two that we talked about of how do we convert it to the tri-stimulus LAB data. It's really important that we're consistent about that. So now let's move on to the color difference piece. So we got to be sure we're using the same calculations. For example, if you're using LAB, there's two. There's something called Hunter LAB, and which came in 1945, and there's C-Lab, is the way we typically pronounce it, from 1976. You'll notice the C-Lab has asterisks next to the LA and B, and the Hunter is just plain LAB. So this is measuring two standard and a sample, calculating their differences for delta L, delta A, and delta B, and you can see you get different results. This is for that same bright red color. You see you get very different results between those two methods. They're both right. They're just different calculations. So again, we're talking about numbers today. It's important we're consistent in which set of numbers we're going to use. And then the same is true when we get to delta E, right? early spectros, the only spectrophotometers, the only thing you were getting was percent reflectance. Those numbers weren't easily digestible. So these LAB and other tristimulus color models, LCH and others, were created to make them more digestible, make them three-dimensional. But ultimately, people want one number. We want to be able to have a number that tells me whether it's good or it's bad. And so there's the concept of a delta E, which essentially means total color difference. Give me one number to represent that total difference. The issue is there's a whole lot of different delta E's. So FMC2, which was the first in 42, Hunter, CIE, and then when we hit CMC from 1988 and the two following, CIE 94 and CIE 2000, all three of those are elliptical tolerances, like we were looking at, to agree better with human vision, rather than the top three delta E values are not as correlated with human vision. So to give you an idea, again, just because somebody says my delta E is this, you need to make sure which delta E they're using, because again, these are all calculated difference values between the exact same two measurements, and they vary greatly. Most of the world is using one of the elliptical tolerances, and you'll notice that those three are actually very close to each other in the results they get. It's the first three that have the great variation across them for this particular color. So we know that we're going to calculate numbers to describe color, and we're using them because they're really required for quantitatively measuring color. You know, it eliminates the human, the psycho, physio part of color. It eliminates our emotion and the fact that our eyes can be tricked and affected by surrounding colors and all those kinds of things. We're going to generate numbers from an impartial instrument, which is going to just report what it measures, right? We also learned there's a wide variety of metrics to use, LAB and LCH and all kinds of different delta E's and all kinds of other things that we can calculate from those. So there's a lot of different metrics to use. So it's really, really important that we ensure that everyone you're communicating with is using the same metrics, the same calculations, to ensure that you're comparing apples to apples. And then third, the human response to the color matters. Despite the feeling maybe that we sometimes get when we talk about color measurement and all the limitations of human vision, ultimately, visual inspection is an important part of a measurement program for one very specific reason. I always state it this way: no person goes shopping with a spectrophotometer in their hand. Right? They go shopping with their eyes and they look at something and they make a decision to buy or not buy based on the quality of the product, and color is a big part of that. Now, color measurement helps you maintain that color consistently and be accurate and precise in doing so and all that, but visual inspection is still an important part, and correlating those things to each other. So with that, we have reached the end of all of the material that we have to present. So on the screen, you'll see some links and information you can use to help us, or if you need us to help you, ways to contact us, see our promotions, follow us on social media and all that. So we'll leave this up while we open it up for questions. So Robert, do we have some questions that we need to answer? Great.
It looks like we already have quite a few questions, so we'll get started. If you have any other questions, feel free to submit them now. So the first question is, does more chroma mean brighter or saturated?
Yeah, that's a great question. So it's one of those questions that's a perfect example of why words are really bad for describing color, and yet we all use them, right? So chroma, its proper definition from CIE is brighter. If something has more chroma, we describe it as brighter, and if it has less chroma, we describe it as duller, right? Practically speaking, when we're talking about a color, if it's more chromatic, it's further away from neutral, and if it's less chromatic, it's closer to neutral. Saturation tends to correlate with that, but not always. Adding more, think of it this way, if I have a bright yellow color, I can add more yellow to my yellow, and it might make my yellow get more chromatic, and more saturated, right? But there are instances where I can add something to make it more saturated, and people will correlate saturation with color strength, which again tends to correlate with chroma, but not always. There are situations where you can add more color, make a color more saturated, and decrease the chroma of the color. Doesn't happen a lot, but it can happen. So they aren't perfectly correlated, but they do correlate fairly well.
Okay. How important is the base material in the deltas calculated for color difference, such as if you change the substrate, how will that impact your deltas?
Yeah, great question. Substrate, we as humans, looking at something can, if we're looking at something that's printed or dyed piece of fabric, something where we've got a substrate with color on it or in it, right? We can typically see some of the substrate maybe and also see the color, and so we could look at two and know, yeah, there's a difference in the substrate there. We have to remember that a spectrophotometer, it's really, really good at measuring color, but it's really, really ignorant about the rest of the things in the world. So when I put the sample up there, that light shining from that spectrophotometer onto the sample is going to penetrate and see the color of, let's say I have ink on paper. It's going to see the color of the ink, but it's also going to pass through that because it's transparent and see the color of the substrate. So if I take the exact same ink, print it on 3 different substrates, and measure them, I'm going to have 3 different colors. And visually, you may too. It's just that a spectrophotometer is probably much more sensitive to that than the human eye is. But the spectrophotometer sees everything that light can interact with and come back to the sensors, and so that includes the substrate. Sometimes it's an unintentional substrate. I say that because you might be measuring something, let's say it's a piece of plastic that's not opaque. If you're measuring that with a handheld instrument and you lay it on your desk and take a measurement of it, you just measured your desk as well as the plastic, and so your measurement that the instrument just detected is a combination of those things. Were you to take that plastic and lay it on top of something different, you'll get a different answer. So substrate always makes up part of what what is being measured.
What is the difference between a 2-degree observer and a 10-degree observer?
Okay, great. So it's 2 tests that were done to characterize the human response to color. The reason they're called 2-degree and 10-degree is that it's the size area of view that the human subjects were using to view color. To give you a really easy example, if you stick your arm straight out in front of you and stick your thumb up in the air, and imagine a circle that kind of follows the curve of your thumb, a circle that size at arm's length is about 2 degrees of view. If you put your hand up and make a circle around your hand, that's about 10 degrees of view. So imagine you have to match 2 colors and each of them fills half of the size of your thumb, or 2 colors where each of them fills half of the size of your hand. You're going to get a different result. There are other differences, like the 2-degree test, which was the first one that was done, was all men. They're trying to characterize the entire human race by testing all men, and they didn't pre-test any of those men for color blindness. So there's a good chance that they probably had a colorblind person or 2 in the test, because 1 in 13 males is colorblind, some level of color blindness. So most of the world uses a 10-degree observer because it tends to correlate a little better with human vision of the average person.
Okay, we have just a few more questions here. While we're talking about observer, is it typical that 10-degree observer values are slightly lower than 2-degree?
That's an interesting question. I don't know that I know the answer to that. I haven't ever actually looked at that, to be honest. If I think about it, potentially, yeah, I'm just thinking about the data of the difference between 2 and 10. Of course, I'm sure, while it may be a trend in that direction, it's probably it's certainly not a rule, right? As soon as we say, yeah, it tends to be that way, then we're going to get one that's going the opposite direction, because it's of course very, very specifically based on the particular color that we're measuring.
Which delta E do most people use?
So by far the most common calculations are the 3 elliptical ones: DE-CMC, DE-94, and DE-2000. My perspective has been that DE-CMC was the dominant one, simply because it was the first elliptical tolerance, so lots of people adopted it. Not a lot of folks switched to DE-94, which came, as you can guess, those numbers mean what years, are roughly what years they got released. So CMC was in 1988, DE-94 6 years later. Not a lot of people changed, because it's not easy to go change all your tolerances, right? You can just imagine the nightmare that creates. But DE-2000 is an improvement, and so we're seeing a pretty heavy shift. So right now, based on what I've been hearing lately, I would guess it's probably about a 50-50 mix that most people are using DE-CMC or DE-2000. That being said, people use those predominantly as their pass-fail mechanism, but we still all use LAB or LCH to describe the difference, because those DE numbers, while they're great for pass-fail, if my tolerance is 1 and I get a delta E whatever of 1.7, it fails, but what's wrong with it? Well, the 1.7 doesn't tell me what's wrong with it. It just says it's too far away. So I have to go to LAB or LCH, whichever one of those I'm comfortable with, to understand why is it failing. Is it too light, too dark, too red, too green, and so on.
What is the best color background to use when measuring plastic parts?
So a couple of answers there. One, traditionally, if the standard answer to that is if I'm measuring for reflectance, right? I'm looking for the light to reflect off the object. I want to put white behind it. In fact, if you look, most of like benchtop spectrophotometers and everything, the sample arm that holds the sample in place, you'll notice is a white ceramic, because we want any light that passes through the sample to bounce off of that white. A perfect white would reflect 100% of that. It's not perfect, of course, but it's the best we can do to bounce the light back through. But the reason I say there's a couple of answers is sometimes you want to be able to use functions that exist in our software or instruments to do what's called an overlight over dark measurement. So you want to measure it once with white behind it and another time with black behind it. And then we can calculate, not only measure the color, but we can also calculate the opacity of the sample, which is critical, because the exact same color at a different thickness or a different opacity looks different.
Okay, there's 2 more questions here, so I'll read these last 2 questions off, and then we'll have to end here for today. What is a common delta E tolerance you see for many manufacturers?
Well, that varies greatly. So let's talk about just one tolerance, or one delta E type, just to be consistent. So let's talk about delta E CMC, since it's been the most common use over the last 10 years or 20 years or whatever it is. So it depends what industry I'm in. In the automotive industry, where color is extremely tightly controlled, because all the different parts of my car need to look like they're the same color and they were all painted at once, I might have a delta E CMC tolerance as low as 0.5. And they are able to maintain that. Maybe they're 0.5, 0.7, all the way up to 1.0. But if I go talk to someone who's doing package printing and using a delta E CMC tolerance, their tolerance could be 3.0. So it could be 6 times larger than what's needed for the automotive. And there's lots of reasons for that, right? Packaging, I might be, maybe I'm printing bread wrappers and it's going to be transparent and the color of the bread's going to change behind it slightly, which is going to make the color vary and all that kind of stuff. So it's not, and not to mention it's a package that ultimately is going to be thrown away or recycled, and it's not as critical. So it varies greatly. Maybe the best advice I can give if somebody's trying to decide what's the right tolerance is that you already know the answer to that. You might not know numerically what the answer is, but visually you do. So the best way to determine the tolerance is pick what tolerance type you want to use. Go get standard with multiple samples that you can visually assess. Hopefully you get some that are good and some that are bad. In fact, you need some of each that are visually good and visually not good. Measure them, look at the values, and you can very quickly determine, oh, we start to say it doesn't look good once we hit about 1.3. Okay, maybe that's your tolerance. That's the best way to build a tolerance that agrees with what you see.
Okay, well, I'll read one more question. How do you evaluate white colors with the spectro? Is it the same process? Is there anything special you have to do?
So there are lots of things you can do beyond. So in a word, yes, you're still measuring it with spectrophotometer, still doing the same measurement. You're still going to probably look at calculating LAB and or LCH and having a tolerance, but for things like whites and lots of other things, there are other calculations, things that are called indices that can be calculated. And the ASTM has created some of these kinds of indices. So there's a whiteness index, for example. There are several ASTM methods for calculating whiteness. And our software, QC software will do that. You can take those measured values. You can even create a tolerance if you need to around that to say, oh, because I'm doing white, I'm not going to get a whole lot of, especially A and B variation probably. I'm going to get lots of L or mostly an L, but I can do a whiteness tolerance. There's a yellowness index. There are indices for blackness and jetness, and there's things like a cinnamon index and a nutmeg index and all these really interesting things that are essentially special use cases because special things are being measured where something is determined to be very important for that. And so in measuring whiteness, which is really trying an indice that favors it being as neutral as possible and as light as possible. It's a different kind of a one number calculation with a focus on something very specific. So you can find more information about those kinds of indices on our website, and if you're using our software, you'll find them in there, all kinds of different means of calculating various, we call them special color calculations. They're all based on the same stuff we talked about today, but they are focused to deliver what you need in those situations.
Perfect. Okay. Due to time, we'll stop here today. Lots of great questions. There are a few questions that we will address offline. I'll have Tim follow up with you. Just want to say thanks to everyone for attending today. You'll receive an email with a link to the recording of this webinar. Thanks again and have a great day.